This video was produced for the use of all students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. This is the second part of a two-part video lecture on marine vessel electrical distribution systems. This is the electrical distribution page from the Kongsberg diesel simulator. On this is the tiebreaker for the engine room. This is the tiebreaker on the emergency switchboard. And then this is your emergency diesel generator, the disconnect breaker. And these would be motorized breakers. Then on the simulator, you have two ship service diesel generators. You have a main shaft generator. You have also a steam turbine generator that uses waste heat to produce electricity. We can compare it in some ways to the Golden Bear main switchboard, and there's some things that I want to point out. Now, on the ship, these three panels are the controls for each of the diesel generators. These are their motorized circuit breakers that would open in case of an overload. Then I believe this upper one here, this is going to be your tiebreaker in the engine room on the Bear itself. And these are motorized breakers. Now, these other circuit breakers are manually actuated, and you should already know that you close them by lifting up on the handle until it latches up. If there is an overload, they will pop to the middle, and the middle position gives you an indication of that it is tripped. And to reset, you pull down to the open position, and then you manually lift it back up again. If you ever have a trip breaker and you pull it down to reset it and then set it back to closed and it immediately pops out, do not energize that breaker again. That means that it's a severe overload. It's doing its job and it's tripping. And if you do that multiple times, not thinking, you can actually cause the circuit breaker to fault, and it can have you can have a flashback or you can have a fire. So just be conscious of that. And then on our system on the Bear, not only do you have a circuit breaker, but you have a fuse block. Now, the circuit breakers for normal overloads, these fuse blocks are for short circuits. In other words, a short circuit is where the power can go to ground, and it can be a very, very large current flow, which could cause a circuit breaker, the contacts, to weld. They can spot weld and not open when you have these extremes. In some cases, you can have as much as 100,000 amps in about a quarter of a cycle. So on our ship, and not all ships are like this, this is a fairly high quality system. You have a circuit breaker for normal overloads, and that would trip to a middle position. It can be manually reset. And then you have these fuses so that if you have an extreme current flow from a short circuit, the fuse will open and protect the circuit. Down on this end, you actually have the 115 volt lighting distribution panel is on this extreme left-hand side of this switchboard. The rest of the switchboard is all going to be 440 volt distribution. This is a picture of one of our motorized circuit breakers. We don't have time to get into this too much, but again, these are designed for large overloads. They can handle a lot of current, and it has two settings. One of them is an instantaneous. If there was a very high current flow, these are set that they would open instantaneously or very, very quickly to protect the circuit. Now, if it's a minor overload, they'll have a time delay before they open. This could be because we are an unmanned ship. This could be that a piece of equipment's been put on the line, and this limited amount of overload would allow a generator to come on the line, synchronize, and put itself on before it tripped. So these are allowed to prevent a blackout situation if you have a generator that is overloaded for a short period of time. These breakers, by the way, can open large current flows. These are typically designed somewhere around 100,000 amp. It can open safely without damage. And to do this, these are motorized. In other words, they have springs that close and open these circuit breakers. And they typically have an electrical motor to do this. So this type of circuit breaker has to usually have an outside low voltage source. It's usually 110 volt single phase that charges up a set of springs that opens the contacts very quickly and closes them very quickly to reduce the amount of arcing damage to the breaker. So we are talking a little bit about the Golden Bear because that is a ship that you're used to, that I know that you've had some experience with. So let's talk a little bit about her main switchboard. So the power is normally provided by 3 900 kW diesel generator sets to the main distribution bus. The main distribution bus is divided into two, and there you have a disconnect link. This disconnect link would normally never be used unless there has been an emergency where the main switchboard has been damaged by a fire. Otherwise, this disconnect link is out of sight, out of mind. The only reason I bring it up to make sure that you understand that these types of emergency services are provided and that you are looking for these types of things. So, bus number 1 contains the generator control circuit battle panel for diesel generator number 1, your shore power, 450 volt distribution section. It has vital engine room motor control centers and 120 volt AC lighting distribution section. 2 has number 2 and 3 generators. The bus tie circuit breaker for the emergency switchboard, supplied 120 volt forward lighting center, and some vital engine room motor control centers and also non-vital motor control centers. So this is a one-line depiction of that. We'll get a little bit of a close-up here in a second. But here are some of the major components being supplied by that. So you've got motor control centers, power panels, fire and general service pump, saltwater pumps. These are all the different loads that are supplied from that. And this is a close-up. So here's the motorized circuit breaker that is on a main generator. And you can see that that one is set to handle as much up to 1443 amps. Then this is your shore power. Each has a breaker to protect it and also the set of fuses that I talked about earlier. And then these are showing the different loads that it's going to. So here's your ship service lighting panel. Again, this is on the far left-hand side. The power comes off a circuit breaker, one of the molded case, somewhere down in this area. I believe it's this one here that goes to a transformer. It is dropped from 440 volts down to 115 volts. And then that has actual bus bars in the back of this. And this distributes the power to all these 115 volt circuit breakers, which are feeding different power panels, lighting power panels throughout the ship. All right, so this is just a depiction of the bus bars. Now, the bus bars are just solid bars of copper that run the entire length of the switchboard itself. And these are bolted together, and they form the main distribution as far as they're designed so that if you have all three generators on the line and they are supplying their maximum load, these bars would be able to handle that full current. So a bus bar is the bus. What we're talking about are these solid bars that are used to distribute electrical power. All right, so you also have motor control centers, and these will have a breaker, a large breaker off the main switchboard. And then there is a bus bars behind these motor control centers, and they have various motor starters arranged on this. So this is how they're kind of segmenting out. Also, you notice that some were going to be vital equipment and some is non-vital equipment. And internal to them, they also have bus bars. And these bus bars will distribute the power to each of the individual circuit breakers. So this is actually what these bars look like in the back of one of these panels. This is actually off the emergency switchboard. And then you have your different power panels throughout the ship, some for lighting, some for small motors, and these also are going to protect those individual circuits. So one thing of note, it is when you talk about distribution, your main switchboard has a very high load carrying capability. And then those has breakers that protect equipment, and the size of the cabling is a determinant on this going to each of these pieces of equipment. But if you're talking of, say, a light in your room, it is first that power comes off the main board, goes to a circuit breaker protecting the transformer, and then you have a circuit breaker off the 115 volt distribution that is going to a power panel, and it has a circuit breaker to protect the cabling to that power panel. And then at the power panel, you have circuit breakers that protect each individual circuit. So one of the things on this is make sure that you know where all these electrical feeds come from. The bear is a good example in that you have all this equipment, electrical equipment that's vital to the ship, and the circuit breakers for each one of these equipment and motor starters are distributed around the vessel. So it's very important, especially if you're asked to do something in an emergency, that you're not having to look and find where that power is coming from. Always be very conscious of this, and I want you looking at this equipment and where it's fed from so that you feel good about yourself, that in an emergency you knew where to go and you knew where to reset a circuit breaker. Now, we want to get a discussion on how important electrical distribution is to the operation of a vessel. And I think a lot of times people don't think about it. Electrical distribution arguably is the most vital system on the ship. A blacked out ship cannot function. If you lose all electrical power, you've basically lost all your control of that vessel. So that's one of the things to think about. This is a vital system. Now I'm bringing up the APL China. The APL China is a container ship, 5,000 TEU, built in 1995, that is in the American flag. In 1998, while in a typhoon, the plant ended up blacking out. Now, the problem with this is that water on the main deck was actually able to hit the louvers that we talked about on their emergency generator, go into the emergency generator space, and was not draining fast enough and got up high enough to knock out the 24 volt distribution bus. When it did that, they lost all automation. The automation is what operates this vessel. It's a very highly automated vessel. So they lost power in a storm. Once they lost power in the storm, that ship is going to lose propulsion, it's going to stop, and then it's going to move and get into the trough, and it's going to start to roll. And I want you to take a look at these containers and look at the damage from the rolling. Now, the reason I'm bringing this up is that with this ship, if they lost their automation, very, very quickly, they had to get this plant back on the line, get their propulsion up and running if they wanted to survive. So you have to have a crew, a very competent crew, that knows how to bypass the automation systems, knows how to, their electrical distribution system, to get this vessel back up and running. And again, it is critical to survival that you do not, that you can bring your power back up in this type of condition. Another example I want to bring up is the Carnival Triumph fire, which happened in 2013. Do not get the impression that this is not a well-run vessel and that had a competent crew, because I believe it absolutely that it did. But they had a fire in their electrical that affected their electrical distribution. So it was early morning hours of October 10th, 2013. A flexible pipe on the fuel oil drain line forward to number 6 engine failed in service. So that is spraying oil into the engine room. The fuel oil contacted a hotspot, resulting in a flash fire that severely damaged ship's diesel generators number 5 and number 6. The main cabling in the overhead in the aft engine room serving the switchboard was damaged, resulting in loss of power from diesel generators number 1, number 2, and number 3. Now, these generators were not damaged themselves. The fire melted down the cable that disconnected these generators from the main switchboard. Number 4 SSDG was undamaged, but it was out of service and opened up for an overhaul period. Prior to ignition, atomized fuel oil from the flexible pipe triggered the fire alarm system. So they got an alarm, and they were responding to the alarm. Several minutes later, a fire erupted in engine number 6, and the high fog fixed water firefighting system automatically started, as it was designed to do. The high fog system you have on the simulator, and it is incorporated into that. And what that does is it has a very fine atomized mist that will not suffocate human beings, but it pulls the heat away from a fire and puts it out. Very good system. But the system failed because when the power went down to the main switchboard, because of the cabling being burned, that cut off power to the high fog system on the control. They had not put it on the emergency, they'd put it on the main. So now they've lost their firefighting. The chief engineer had ordered all the fuel system quick closing valves to be operated to shut down the fuel to the fire, and the permanent fixed CO2 system was discharged into the aft engine room. That is actually what ended up putting the fire out. So this is number 4, and you can see what a generator would have looked like before the fire. And the other thing I want to point out, that you have 6 generators, 1, 2, 3, 4, 5, 6, and 2 engine rooms, an aft and a forward. The source of the fire was right around here in number 6. So only these 2 generators were damaged actually by the fire. But unfortunately, on the forward engine room, the power cabling from these generators was in this overhead, and it burned, and so they lost all their generators. So this is a look at the fire damage. On the left, that's to the number 6 generator, and on the right, that's your cabling supplying power to the main switchboard. So let's look at some of the factors that were very instrumental in going from a minor incident to a major incident in this fire. The vessel suffered a total loss of main electrical power and propulsion. The high fog system, the primary one that would have shut down this fire very quickly, lost power because of the wiring was burned and power was cut off to the main switchboard. There was a problem with their CO2 distribution valve, so they had to manually go down and dump CO2 into the engine room. They couldn't do it remote. They had a fire hydrant fail, causing flooding. The fire hydrant, the diaphragm blew out on it, and it caused flooding in the engine room. The emergency generator experienced a fuel leak, cooling problems, and had difficulty coping with the power design. So not only did they lose all their generation capacity in the engine room, when their emergency diesel generator, was operated for a long period of time, they found that it had different problems and they were having difficulty keeping power onto the emergency board. So the vessel also developed a list due to the free surface effect from flooding. So here you have a ship with 6 generators, 2 engine rooms, and they had a catastrophic failure as far as this ship floated for days without power. So I want you thinking about how important the automation and this electrical distribution system is to your life. Now, the other thing I want to talk about is unattended machinery space. Almost every ship produced today is set up for unmanned status. That means no one's down there from basically 5 to 8 in the morning. The ship has enough automation that it will control, all the control functions are done by the automation system. The humans are there to monitor and to respond to any problems and alarms. So under UMS operation, you have to have automation alarm systems capable of monitoring all your major systems. You have a watch call system where you can select which engineer is on call, so that if there's an emergency, that will notify, just an alarm, then it will notify that engineer of what alarm has, so that engineer can come down into the engine room and respond to it. If the watch engineer does not respond back with the watch call system, then it will typically notify the bridge and the chief engineer of a failure, that the engineer failed to respond to the watch call. You also have to have a power management system and a fire detection and suppression systems. All have to be in place for unmanned status. So on the Bear, which you are used to, you have these screens which are called the Human Machine Interface, HMI. And this is a distributed control system. You have a network that goes within the engine room and that brings monitoring points and temperatures, pressures, levels into the computer system. And you can monitor, and it has control. It can control the different systems, specifically on the Bear, a lot of main engine controls. And then you as an operator can look at these screens and use that to determine your alarms and all your alarms and temperatures and pressures. Now, on this has a menu system. A distributed control system typically has menus that you can look at each of the different systems, and you're very familiar with this. So the majority of your information on modern ships now is coming through these HMI units. And most of your control, there are ships that's specifically that you go through the computer systems for controlling the vessel. And it has to be that way because this engine room has to be able to operate on its own when humans are not in attendance. Now, if you go into the back of the main console, you'll see this computer here. This computer is only running those displays. It actually has programmable logic controllers, PLCs, that run on a network that are controlling the vessel itself. These computers are just a ruggedized industrial computer that has taken information off of that PLC network. These are what the PLCs running that vessel, the Bear, look like. Okay, so on the watch call system, you can take and you would set this up whenever the ship is unattended. One of the engineers would be selected, and then the system will call them whenever there is an alarm. You also have to have a power management system, and the Kongsberg diesel simulator has this, and that power management system will automatically put generators on the line and take them off the line without any human intervention and to maintain the capacity of the system. In other words, if your load on the system gets too high, it will automatically put a generator on, and when the load drops back down, it will take a generator off. And you're going to set priorities, which generators that you want to be your primary, which is your secondary. All of these features are put into this, and we'll be talking much more about this in class. On the Bear, you do have a power management system, but we elect typically not to use it. It uses a Woodward system that is in the main switchboard. And this system is perfectly capable of putting generators on and off, synchronizing them, paralleling together, all with no human intervention. Preferential load shedding. One of the things that can happen, it's in the middle of the night and the mate goes out and starts up the crane on the stern of the Bear. That's a big motor. It pulls a lot of current. And let's say we only had one generator on the line and that generator is fairly heavily loaded. All of a sudden, with that additional load, now it goes into overload. So typically what will happen on that is that if there is, if it's a minor amount of overload, then the motorized circuit breaker, the disconnect circuit breaker for that generator can overload for a short period of time while give the other generator, the standby unit, time to come up on the line. If it's more than that, then you have these preferential trips. What the preferential trip does is if there is an overload that could cause a blackout situation, right? It will detect that, and if there's not enough time for the other generator to come on the line, it will shed these non-essential loads. Those are going to be things like your air conditioning and different loads that if they trip will not endanger the vessel. And by tripping these loads, then what will happen is that you give that generator, you reduce the load on the generator to give another generator more time to come on. But that also means that you as the operator are going to have to go down and reset all these equipment. And these are called preferential trips. So each generator is supplied with overcurrent relay, which will trip the generator disconnect at 150% of normal rated load, and it's got a 20-second delay. So in addition to the overload relay, a preferential overload trip is provided to shed non-essential load during minor generator overload conditions. And these are the first stage on the Bear, which is air conditioning, galley, laundry, and then there's a secondary. All right. So this concludes this electrical distribution video. I hope it has been informative. Thank you very much.